Hello, everyone. It's a pleasure to be here. I believe it's my fourth time attending, so it's an honor to be presenting at this summit. So thanks for your time and attention. Oops. I'm personally and professionally motivated by technologies and systems designed to serve the most marginalized, and I sometimes use the United Nations Sustainable Development Goals to assess these technologies. Creating and using biochar is one such technology. Specifically, if we think in the context of source separating toilets, where we gather urine and feces, that feces can be converted to biochar, or biochar can be created using other feedstock, then used to recover nutrients from urine, specifically nitrogen, to create a nitrogen-enriched soil amendment, which can be applied to agricultural soils. And this process can create the biomass, which can eventually be turned back into biochar. This is tangential to the system Lucinda Lee presented on yesterday, so I'm excited. It's exciting to see the different dimensions of such a system. One of the limitations to this system that I choose to focus on stems from the knowledge that biochar and thus biochar systems and responses are highly variable. Specifically, I'm referring to biochar's sorption of nitrogen, like the ammonia present in hydrolyzed urine. This variability is because biochars can be made from many different feedstocks, different pyrolysis methods and parameters, modified physically, chemically, or biologically pre or post pyrolysis, and then characterized in many different ways. So it's almost no wonder we see large variability in biochar sorption of nitrogen. We see sorption capacities reported here on the y-axis in milligrams of ammonia per gram biochar that span orders of magnitude when looking across different feedstock types. Over the years, we've been converging on the concentration and protonation state of biochar's functional groups, exerting strong influence over its sorption of nitrogen. These functional groups can be measured in different ways. Some are shown here on the left, but much of the available literature that is able to relate these functional groups, however they are measured, to nitrogen sorption studies simple ammonium solutions. Excuse me. Urine is more complex, partly because it exists at a pH where both ammonium and ammonia, or total ammonium nitrogen, are present, and because it has a high buffering capacity, mainly due to its total ammonium nitrogen pair, and it has a high ionic strength. These factors, which would interact with biochar chemistry in ways that distinguish total ammonium nitrogen, or TAN, sorption behavior in urine from simpler ammonium solutions. So given this wide variability in sorption capacity, prevailing evidence on the role of functional groups, and the limited studies on urine specifically, I sought out to understand how the concentration of biochar functional groups influence its sorption of total ammonium nitrogen from hydrolyzed urine. I chose to focus on three key aspects that would address the variability we see in existing studies, as well as make the results more representative of full-strength urine. These include studying a diverse suite of biochars, using multiple ways of characterizing biochar functional group concentration, and studying sorption dynamics under conditions that are representative of hydrolyzed urine. I focus on these aspects to be able to assess the effects of functional group concentration, regardless of all these factors that influence biochar characteristics. In total, I look at 4 different feedstocks, 2 different temperatures produced in 2 different ways. I oxidize my biochars to create a set of 19 biochars with a range of functional group concentrations. And I analyze the concentration of functional groups based on the bulk oxygen to carbon ratio, or O to C, the surface O to C, and the proton density. Or proton density, which is also the concentration of proton active functional groups. Proton density is based on direct, either acid or base titration of the biochars, as depicted in the graphic here of our system. And what we see from our titrations when we look at the proton density on the y-axis and the pH on the x-axis, and also the bulk O to C gradient from low in orange to high in blue to systematically distinguish the different biochars, is that majority of the functional groups had pKa's and buffering capacity in the pH 3 to 7 range, and thus would be deprotonated at urine's pH. We also see from looking at the neutralization plot, this time with the change in pH per mole of titrant added on the y-axis and pH on the x, is for more oxidized biochars, we see a continuous distribution of proton affinities across the pH range, suggesting an increased diversity of discernible proton-active functional groups. What this means is that direct titration may be able to sufficiently both quantify the concentration of functional groups, as well as discern the diversity in functional groups across biochars. To be able to relate proton density as well as other measures of functional group to total ammonium nitrogen sorption capacity, we generated urine sorption isotherms in batch experiments. First, by diluting urine and equilibrating it with the 19 different biochars. And when we look at the sorption density on the y-axis, a millimole of TAN per gram of biochar as a function of the TAN concentration, which is represented on the x-axis as equilibrium activity, because activity takes into account ionic strength, buffering capacity, and pH. We see that the sorption density starts to plateau as we approach the concentrations of full strength urine, which is the Langmuir-like isotherm. We also looked at sorption isotherms by changing the dose of biochar and equilibrating it with full strength urine. And what we see here is an increasing sorption density as we approach the concentration of full strength urine. While this behavior is intriguing, the cause of the high sorption density region, after exploring some mechanisms and reanalyzing some published data, remains unknown. And this warrants further investigation because verifying this behavior and identifying the underlying mechanisms driving the behavior could have important implications for optimizing biochars for total ammonium nitrogen recovery from urine. The main takeaway is we can say that across the 19 biochars studied, biochars are able to recover total ammonium nitrogen from hydrolyzed urine. To be a bit more quantitative, we correlate these sorption densities across the multiple ways we characterize the biochars and find strong correlations between the functional group measure and sorption density. These correlations hold true whether we are looking at sorption densities on the y-axis as a function of the bulk O to C ratio on the x-axis, the surface O to C ratio, or the proton density, as well as whether we are looking at the sorption densities from diluting urine or from changing the mass of biochar. And what we're able to say from all of this is that if you have biochars with a bulk O to C, surface O to C, or proton density within these ranges, you can expect a biochar sorption capacity, sorption density within this range. And the main takeaway is that these three independent measures of functional group concentration directly correlate with total ammonium nitrogen sorption across biochars. To reiterate the main takeaways across the study, I summarily say that direct titration distinguished functional group concentration and diversity. And more broadly, one can use acid and base titration of biochars to identify functional group concentration or acid and base titration, or any of the three measures presented here, maybe based on what is accessible to identify optimal or rule out suboptimal biochars and simplify biochar selection for 10 recovery from urine. Lastly, I'd like to first thank those who chose to invest in my education and professional development in many ways. And I'd like to note that there are a decent amount of people working in or who have worked in Kenya and across the region. And I'm currently based in Nairobi, Kenya, and along with some wonderful folk, including some at Cornell who are part of this summit, we've created the Circular Bionutrient Economy Network and have been working over the years to bring together circular bionutrient economy people and resources regionally. We'll be hosting a joint conference with the International Biochar Initiative in June of next year, and I placed a link here for more information. And I'm also working with the World Agroforestry Center, or C4ECRAF, on some predictive modeling of biochar characteristics using spectroscopy. And I'm submitting my dissertation at the end of this academic year and starting to put my next steps in place. So if any of this sounds intriguing enough to discuss further in future research endeavors, please reach out. Thank you for your time.